welcome to our project of Abhi and Aditya, and we chose to model the Black Friday purchase problem to predict purchase prices given a variety of factors. So just for a quick background, Black Friday is one of the biggest consumer holidays in the United States, and companies for years have been figuring out what sorts of products to mark down and what sorts of products to market to customers in order to increase and optimize sales. And obviously, as I'm sure you know, customers in droves flock to a variety of stores in order to buy products that are severely discounted. So the uniqueness of this problem and the significance of it to the consumer market is what really drove us towards attempting to crack this problem. And the data that we used was actually from a machine learning challenge on a website called datahack.com, and it's extremely well maintained. There's about 550,000 rows and 13 columns filled with interesting variables such as marital status, gender, stay in city, occupation, etc., with the idea being that these variables are important indicators of what people buy and what sort of products that they buy. So in order to approach this problem, we are using two types of learning. The first is the classic OLS, the ordinary least squares method, in which you're running linear regression in order to predict the purchase price. And the second model that we decided to go with was a decision tree classifier in order to see if the model reacted better to going down various routes given certain categorical variables. The performance metric P that we've chosen to use here is RMSE, which is root mean squared error, and this basically takes the difference of your linear model residuals, finds the mean of it, squares it, and then takes the square root. And the value of this is it tells you how close and correct your model's predictions are.
Doing a little bit of exploratory data analysis, and initially we just wanted to get a better idea of how the data was formatted, the structure of it, and what all the columns had in them. And as we looked at it, we realized some of the columns had some null values, so we wanted to take a deeper dive into this. Once we actually got the information on the data set, we realized the only two columns, with null values were product category 2 and product category 3. And this kind of makes sense, as product category 1 was the most general product category type, so not all the products would have a second or third category. And every other column had no null values. After that, we wanted to get a better idea of each column and see actually how many values we had for each bin in the columns, because these were all categorical variables in the end. And the first thing we graphed was age. Now this was really interesting, as the age range of 26 to 35 had a disproportionate amount of people in it compared to all the other age ranges. And we thought this might mess with our model, as we could get really good at predicting the prices, the purchase amount of people within the age range of 26 to 35, but might be less accurate with the other age ranges. However, after doing some more research on the US Census, we realized that this kind of modeled how the population of the US was, as 30% of the entire population in the United States falls between the age range of 26 to 44, and this was kind of how our data also looked. So we decided to leave this and not normalize any of the values. Next, we kind of wanted to look at the cities the people came from, and there are 3 cities, A, B, and C. All these values, by the way, such as product category, city category, and so on, were masked, so we really didn't know what they mapped to, but we could kind of see how many data points were available for each one. Here we saw there were more people in city B, but not enough to change the data set in any way to minimize this. Next, we look at gender, and we saw that there was a lot more males than females, but if we wanted to make the data set more even between the two, we would be losing a lot of data points, and we decided not to do this. Then we looked at product ID. At first, we thought product ID would kind of be unique, but that was not the case. That there was a lot of same products being sold, and we wanted to get an idea of how many of this would it be worth splitting these up into more columns. And finally, we decided to get some summary statistics of the data set, and while for a lot of these it did make sense because they were all categorical variables, the one that actually made a lot of sense was purchase amount, and this gave us the mean, standard deviation.
So the first model that we tried to run here was OLS, and the first thing that we did was we actually used a useful pandas function called getDummies to convert all of our categorical variables into dummy variables that made it easier to encode for the purposes of running the regression. Then we went about splitting it as a standard procedure into training and test sets, and that was done right here, and then we dropped the purchase and product ID. The reason that we did it in this first run through is that we felt like, first of all, the product ID would have been a dead giveaway as to the purchase amount, and the purchase amount was what we were using for our test labels. Then we fitted the model, and then we used it to predict the regression, and we actually got a model score of 64.8. So what this actually means is that the r-squared value, which is the amount of variation in y that is explained by x, was 64.8%, which at the beginning is a pretty encouraging performance for our test labels. As you can see, this is a scatter plot of the predicted versus actual model values, and you can see that it has a general upward trend, and so we felt that our line of best fit captures this trend pretty adequately. So for context, the standard deviation of our test labels was 5,023, which means that the average purchase amount deviates by $5,023. And this is really encouraging here because, as you can see below, the root mean squared error of our model was $2,982. And what that means is that our model is predicting the actual values really closely, because the root mean squared error is way below the standard deviation, which means that our model is actually learning something and using that to spit out accurate predictions. So the next thing that we tried to do was run another linear regression, except this time we kept the product ID. And our thinking behind this was that since the data set was aggregated over multiple years, there would be different markdowns on the same product ID over different years, so it's not a dead giveaway for purchase price, and instead it's just another accurate feature that could probably make our model better. And so we followed the same thing, except this time for the purposes of efficiency, we encoded our values into sparse SciPy matrices so that our model didn't take too long to run. And running OLS increased our r-squared value slightly to 66.4% and decreased our RMSE by about 100 points to 2,906. We then tried a different sort of regression model, and that was the decision tree model. And we found that this model wasn't really accurate for predicting what we wanted to do, as we just got an r-squared of 52.9%, and then our RMSC went up by nearly 500 points to 3,439. So just for the purpose of experimenting, we left it in there to see what models fit, what models didn't, but we decided for our final test to go back to OLS, and this time we also dropped user ID. And dropping user ID yielded great dividends. So when you run the model the fourth time, we actually got an r-squared of 72%, which was a 6% markup from our second model and an 8% markup from our first model. So really encouraging. But the actual key finding here is that our RMSE was 2,671, which was a $300 decrease from our initial two models. And this is really fantastic because it shows that our model, as we engineer more features and figure out what to keep and what to drop, shows that our model is getting better as it goes on.
We were trying to analyze was how can we accurately predict purchase amount based on a bunch of categorical variables about the user. And this is actually a very important problem to solve, as it can help companies determine a lot of things. However, since a lot of the categorical data we had was masked, we don't really know what this the max values map to, but the company that released this data set does, and so they can use this to effectively target certain groups based on products and purchase amount. One of the main benefits of this is that the companies can figure out how much to mark down a product while still being able to make the most money. Since this is a Black Friday data set, and where a lot of this is a day where the most sales happen, the most aggressive sales happen, if a company marks down their product too much or too less, they will take a big loss, and finding the right amount to mark down the product while still being able to make the most money is very important. Companies can also more effectively target certain groups of customers based on their willingness to pay. Since now we know how much a certain group of people are willing to pay for a product, they can have better targeted ads and can expect sales to go up since the right customers are becoming more aware of their product and sales happening. And lastly, the last big benefit of this is that companies can figure out which products to actually stock up on for big sale events. By figuring out which product types customers are wanting to buy and how much they're willing to pay for them, companies can select the perfect product mix to maximize sales and maximize profits, and this will also make the customers happy because it'll make the customers feel like the companies know what they want and how much they want to spend on it.